Hi, everyone. Welcome to this webinar about the future of data integration with a special focus on Oracle GoldenGate for data mesh, stream processing, and a deep dive into Apache Kafka patterns with database events. My name is Jeff Pollack, and I'll be your speaker and host today. For those of you that haven't done one of these webinars with us before, there's a chat area here in Zoom where you're welcome to place questions. We have a few other folks from the Oracle team monitoring the chat, and hopefully we'll be able to get to a number of your questions there. And then at the end of the presentation, assuming we have a few minutes left, I'll certainly hang on the line and take any verbal questions that come up. So thanks for joining today. This presentation today actually follows Oracle policies around safe harbor. We may be discussing futures today, and there's no real specific guarantee on specific topics that we cover and kind of any delivery promises around that. So just be aware of those safe harbor policies. For our agenda, we'll begin with a look at the significant and strategic forces that are shaping IT around IT data management. In particular, the drive towards distributed data processing. Next, we'll provide a quick refresher on the Oracle GoldenGate area and how that fits with this modern data approach. Then we'll deep dive into some very interesting patterns that we're seeing from customers who tap into database change events and propagate them into big data streaming environments like Apache Kafka. And finally, we'll wrap up with a quick look at the stream processing capabilities that come with GoldenGate. So let's go ahead and jump right in. You know, there's quite a bit being written these days about futurism and how the forces of high technology are shaping society and the IT systems that our companies depend on. Some say that, you know, data is the new oil, while others are saying, no, you know, data is actually more valuable than oil because it's an easily renewable asset. But one thing that seems pretty clear is that there's a real paradigm shift occurring as the old ways of computing evolve into what Klaus Schwab calls cyber-physical systems, where digital and data drive this shift into a fourth industrial revolution. It's become almost cliche to talk about digital transformation these days, but Kevin Kelly here in his book makes the case that this paradigm shift is actually inevitable, that the survivors and winners in this new economy will be the companies that learn the key lessons around sharing, decentralizing, and connecting information assets across boundaries. These lessons about data management are essential for the processes of innovation. The old paradigms that have been in place for 30 years draw upon monolithic concepts of data management that affect the way we organize people, processes, and technologies that we've invested in. The root issues are that these older monolithic ways of thinking and organizing teams are not sufficient to modernize IT or accomplish digital transformation. Modernizing data management requires looking at people, process, and technology. So the people, process, and technology components are inexorably linked together. A centralized monolithic technical solution often drives centralized and monolithic organizations and team processes that look after those monolithic technologies. We believe that the market is going through a fundamental transformation right now around data management, away from the more classical data management architectures like Inman, Kimball, Lambda, and CAPA. These legacy architectures are like monolithic mainframes. They got the job done, but they were too centralized, too brittle, and too expensive. The future of data integration will move towards a distributed architecture that can run on any cloud or at the edge of the cloud. Borrowing from service mesh concepts of microservices and Kubernetes, we call this a data mesh. This shift from Industry 3.0 to Industry 4.0 will bring a lot of changes. We're going to see a lot more focus around event-driven streaming solutions, service mesh deployments in Kubernetes that are centrally managed but can run from any cloud. And we'll see data that can scale on demand and be processed from the edge. Individually, any single one of these technology shifts might simply be seen as an evolutionary step, but taken together as a whole, what we're really witnessing here is a complete paradigm shift at scale. In a conceptual view, the organizing principles for a data mesh are around end users working with data domains. These data domains are the driving purpose of a data mesh because these domains enable the creation of what we call data products. It is the data products that the business owners care about, and it's the reason that IT is funded to provide this whole infrastructure in the first place. Modern data infrastructure must be event-centric and driven by the needs of the data consumers. We can use change events or application events to propagate data anywhere in the world, and stream processing engines can perform data integration in real time in micro batches and even with batch processing. Data will be made available as canonical business objects, as prepared data and flattened views, and also as the raw data formats that are being emitted directly from the producers, the data producers. These different data formats will be consumed by business users, analytics users, data scientists, and DBAs. The whole architecture is designed to be distributed from the ground up. There's no central processing engine. In much the same way that containers and Kubernetes can be used to mesh services across different servers, a data mesh can mesh data across different data stores, regardless of whether they're in a public cloud, a private data center, or at the edge of a 5G network. Once fully realized, data of any shape or format can flow anywhere it's needed instantaneously. The GoldenGate platform that we are building today encompasses a holistic solution for data connectivity, movement, data integration, streaming pipelines, and a fully governed ecosystem that also supports a data catalog, data lineage, and data quality controls. The latest versions of GoldenGate 19.1 already deliver a microservices architecture for geo-distributed deployments, Veridata for data governance, and GoldenGate already includes a full-featured stream pipeline engine for real-time data integration and pipeline lineage. You might not have been aware of the full platform capabilities of GoldenGate, but that's one of the purposes of this webinar today. The GoldenGate vision for this data mesh is to provide a single pane of glass for development and operations of all aspects of the distributed data system. Components may be physically at the edge of the network, but will be managed in a uniform manner. Data will flow on an event-driven basis for both change data capture as well as for bulk processing. This is what we're calling a distributed CAPA architecture. As things stand today, we are substantially down the path on this vision already. We have the core GoldenGate microservices foundation that helps DBAs and data engineers replicate data events across any global network. And we have a world-class stream processing engine that empowers data analysts and data engineers to create powerful data pipelines, time series analytics, and directly embed production machine learning algorithms into real-time in-memory data streams. Our customers use these capabilities right now to get data in the right formats to the right people at the right moments in time. So next up, let's take a quick look at GoldenGate and GoldenGate for Big Data. The core GoldenGate platform is an enterprise-class tool with more than 7,500 customers globally, depending on it every day for data replication at massive scale. GoldenGate obviously supports Oracle technologies, but there are more than 500 unique combinations of data sources, platforms, and software versions that Oracle GoldenGate can support beyond just the Oracle platform technology. GoldenGate for Big Data is the packaging that bundles together the support for all these big data technologies and streaming capabilities. This has been one of the hottest areas for GoldenGate in the past 5 years because it is an industrial-grade solution. Oftentimes, after our customers have tried open source frameworks, ETL tools, or smaller CDC vendors, they typically come to GoldenGate when the business is ready to get an industrial-grade solution. Likewise, another reason why we've seen a surge in GoldenGate for Big Data is that customers who are deploying data science solutions quickly realize that it's simply not sufficient to depend on ETL solutions. GoldenGate is an event-driven solution that tells the whole story of your data, the entire story of your data, data flow, your change data. Imagine trying to understand a book by reading every 24th page in the book. That's what it's like to try to understand your customer's behavior while looking at data in 24-hour snapshots that ETL batch processing typically provides. In this case, GoldenGate provides that change stream that shows you each and every event ordered in the correct sequence across an entire day or an entire year of user behaviors. As expected, GoldenGate for Big Data works with all the normal GoldenGate products for relational databases. It also includes a variety of supported sources like Java Messaging Service and Cassandra. GoldenGate for Big Data also provides a huge variety of support for targets like big data, NoSQL, cloud, and other streaming targets. And of course, we also include the stream processing capabilities for free when the data source is GoldenGate. The streaming capabilities empower our customers to take care of ETL operations in real time, correlate data event streams in real time, as well as do alerting, time series analysis, and spatial analytics as part of that streaming data platform. All of this adds up to a very broad set of capabilities that you can do with GoldenGate for Big Data. It can support your data lake use cases, can support your cloud use cases, it can support your NoSQL use cases. You can create streaming data pipelines for ETL, you can perform time series analytics, and you can embed machine learning into your real-time data flows. All of these capabilities are empowered by the GoldenGate for Big Data product area. GoldenGate for Big Data supports writing data into all of our big data formats, into all of our big data targets in a variety of different formats, such as Avro, JSON, Parquet, and others. So over the years, we've been adding multiple formatters. Some of them are native to the different target technologies, while others are more standard formats that are commonly used industry-wide, JSON and Avro being two of the very typical ones that we see. But we can also, of course, support common delimited files in XML and others. Those are all included in the baseline functionality for GoldenGate. A very common use of GoldenGate for big data is to add on to existing GoldenGate deployments. More than 7,500 customers in 180 countries already use some GoldenGate today for relational database replication. And it's actually very easy to tap into these existing deployments. With GoldenGate, you can capture once and replicate data everywhere without any additional impact on the source systems. One significant reason GoldenGate is a nice pairing with many of the big data and NoSQL systems is that GoldenGate is a trusted resource for providing transaction-safe consistency with the same levels of reliability that relational databases have. As many of you may already understand, the big data technologies are not always consistent with transactions, with data transactions coming from relational databases. And for some use cases, involving money, for example, or e-commerce, this can be a very bad thing if you're trying to perform analytics in an environment that isn't actually preserving the transaction boundaries. While maintaining those full consistency guarantees, GoldenGate provides parallel apply capabilities to optimize throughput on very high volume event streams. Since GoldenGate is fully aware of the source side commit boundaries and dependencies, it can reliably partition data for parallel inserts on the targets, whether that's Kafka or other big data targets. This coordinated apply capability applies to every technology that we support in the GoldenGate for big data packaging. And finally, it's worth mentioning again that GoldenGate is prototypically used for high availability and disaster recovery on very high value banking and banking systems and global payments platforms. So the same kind of trusted, highly available architecture that we use with the core Oracle GoldenGate capabilities can also be used to ensure 24/7 availability of the GoldenGate for big data architecture as well. That's one of the benefits of having that core technology foundation providing high availability and disaster recovery for database engines themselves, is that when you carry the technology over to big data, you get those same fundamental characteristics that you've already begun to trust over the years on the relational database side. All right, so that brings us to the next section, a deeper dive into some very interesting patterns that we see with GoldenGate and Apache Kafka being used together. So Apache Kafka is actually just one of the approximately 20 or so target systems that are supported by Oracle GoldenGate for big data, but it's undoubtedly one of the most popular target technologies that we see. Within the broader Kafka technology domain, we also include support for the fully open source Apache distribution, as well as Confluence distribution of Kafka. We support the Amazon Managed Kafka Service, AWS Kinesis, obviously Oracle Streaming Service, which is Kafka compatible, and we also support and are fine with many other Kafka compatible distributions, or even cloud services provided by other public cloud vendors. So you can use this GoldenGate for Kafka integration across a pretty wide set of technologies in the industry. A general problem that many of our customers are trying to solve by bringing Kafka into their architecture is how to efficiently reproduce transactions from the application system of record into a highly scalable publish and subscribe framework, which can then be used to serve data downstream to different data consumers. Right. So in the context of most data-driven applications, it can be quite important to produce transactions that are known to be committed and consistent on the system of record, which is one reason why database logs are an ideal location to produce transactions from. In a data-driven application, for example, the database log is the ultimate record of truth. This is what's used for backup and recovery services on the core applications themselves, the core databases, and really the primary system of record for the business data that's being transacted in the source application. And so that's really when we see our customers looking for a change stream-based solution to bring database transactions into Kafka. This is one of the reasons why you want to go against the database logging infrastructure versus any of the higher tiers, for example, in the application tier or in the higher level of the database tier. The database event log winds up being the ultimate system of record for recoverability in most situations, and that's exactly what we provide. So in this section of the presentation, I will touch on a number of patterns that we see our customers working with to accomplish their objectives. We're going to take a look at how to preserve transaction consistency across these environments. We're going to look at different approaches for table and topic mappings. We're going to take a look at how to work with change streams across a change data capture framework into a messaging framework like Kafka. And then we'll take a brief look at the end. I'll probably move through fairly quickly, but we'll take a brief look at the end around different physical deployment topologies that we see for running GoldenGate with Kafka and how that might typically look as a hosted framework. So to begin with, it might seem trivial to say this out loud, but it's worth being very crisp about in this presentation. Sometimes people get confused, but it's worth saying that Kafka is not a database, right? If you have a business need and you have a use case that's a better fit for a relational database, you should probably use one. Kafka does not maintain internally consistent transactions across topics in the same way that a database maintains transaction consistency across tables. Nor does Kafka provide a declarative query language for fetching and joining tables across topics. At the end of the day, Kafka is not a database, and I think you want to take a careful look at your use cases and make sure that you've got the right kinds of service levels and expectations around your use case without trying to fit a square peg into a round hole. In fact, it's only been pretty recently, the last couple of years, that other big data technologies such as Mongo or even Apache Hive have added their own levels of ACID compliance in terms of maintaining transaction consistency. GoldenGate is, of course, certified with these approaches, and we have many customers using these technologies for many legitimate use cases that combine the technologies. But generally speaking, if you find yourself trying to shoehorn transactional database semantics into systems that are not transactional databases, you may want to consider double checking your technology selection criteria. It's worth kind of pointing that out up front. But again, I think that the general problem that many customers are trying to resolve is how to preserve some of those transaction semantics when you move the data into messaging frameworks like Kafka. So with all of that being said, there are many benefits to Kafka, such as publish and subscribe messaging, the horizontal scalability, the rich community support around connectivity and management. The REST-based infrastructure for Kafka is an ideal framework for providing messaging-based data services at very broad scale. So it's natural that many customers would want to put transactions into Kafka. It's an ideal framework for the broad dissemination of data as a service. GoldenGate is a natural partner for Kafka here. GoldenGate's DNA is as a reliable transaction-safe replication framework, and it's natively aware of transaction boundaries such as SCNs. And internal to GoldenGate, we use our own CSN clock for keeping transaction ordered and grouped together correctly, regardless of which database vendor is producing the transactions. I think everybody here probably knows that GoldenGate is a heterogeneous tool. We can capture log-based events from most databases out there, and the specialty is really transactional databases. So that internal CSN clock that GoldenGate has built over the years, and the one that's what basically drives a lot of our availability and disaster recovery characteristics, that winds up being very useful in the context of propagating transactions into Kafka. So all that GoldenGate metadata that GoldenGate is aware of in the transmission protocol is available to be placed into downstream Kafka topics. Typically, this SCN information and information about updates and deletes are included in messages so that the downstream consumers on the Kafka side can reliably interpret the transaction semantics that might have occurred on the upstream system of record. So, all of that's kind of baked into how GoldenGate sends data into Kafka, and any of that metadata that GoldenGate has can be used to quote unquote decorate the additional supplemental metadata into the Kafka messages. So that winds up being, again, very useful for downstream consumers. The most common pattern that we see as far as mapping with replication to Kafka is basically mapping tables to topics. This is also the default setting for GoldenGate. For many, in fact, for most of our customers, it makes sense to view topics as tables and row-level data events as messages within the topic. So subscribers can easily monitor their tables as topics, and they are notified of inserts, updates, or deletes that happen directly on the table. And so you sort of have this logical association of the schema of tables mapping into a grouping or collection of topics on the Kafka side. All database schemas evolve over time. That's just a normal part of database schema management. So it's important to account for that in the alignment of GoldenGate to Kafka, particularly as those source systems change. Sometimes we call this data drift. Typically, there are two approaches that may be used to help here. The first approach works best when you specifically want alerts on schema changes or when you're not using a Kafka registry. So GoldenGate can be set up to monitor the DDL events on the source and place messages in a type of shadow topic that is recording DDL events on a given table. So maybe you've got two sets of topics for each table. You've got one topic that is basically preserving the DML, the inserts, updates, and deletes, and then you've got another topic that is preserving the DDL, so the alter table operations that are happening on that. And then you can have a different set of consumers or subscribers, some of which may care about the DDL events, others of which may not. For example, if the signature that of the data that they're consuming has not changed and they don't care about the additional data that's maybe being added. So that's certainly a pattern that we see. There's a second approach that GoldenGate has, which is tied in with the Avro capabilities of the Kafka environments. And so this GoldenGate capability basically evolves the messaging framework so that as the schemas change on the source side and the Avro messages are then added to the existing topics, the handler on the Kafka side may update the schema registry when that's available, and so that the change of the message structure is actually recorded in the registry itself, so that consumers that are using the registry will be aware of those message format changes that have been posted to the registry. So another data mapping approach that we've seen in some cases is to place all table changes into a single topic. This can actually work pretty well for you if your downstream Kafka consumers are typically key value pair stores. So for example, NoSQL engines that are mainly interested in the whole system of data events, sort of without needing to preserve the tables or topics. For example, what we see is a lot of search style applications where there's a separate crawler process that might be generating its own index, or where there's a dedicated consuming application that's basically reading tuples from a KVP structure and regenerating the data structures in the application side. And so in that context, you're mainly using Kafka really for its messaging services, and you're not intending to kind of capture any of the model in the registry or in the topic structure as well. So this is certainly an approach that we've seen a number of our customers use. Again, I think it depends on your use case. This particular approach is not really great at all with preserving any type of transaction consistency, or at least it would be very difficult to reconstruct that on the back end. Which leads us to the final pattern I'll mention today around mapping. This is pretty rare, but we have had a few customers talk to us about this, and this has been brought up. This pattern has been brought up when the producer database has very complicated transactions that might involve many tables being updated at the same time with complex key relationships or even long-running commits. In these cases, there may be some advantage to grouping Kafka topics by the specific transaction boundaries that you're interested in. So if there's client updates or product updates that are a particular type of important transaction, you can basically group all of those table events into a single topic, and then that becomes your transaction boundary. And so within the context of that topic, you can basically force the correct ordering within complex transactions or long-running commits, so that your consumers on the Kafka consumer side will basically see those messages grouped together in a single topic, and the sequence of the updates will always be guaranteed to be in the correct order. So that's something that we've certainly seen some people experiment with in the context of particularly complex and important transactions. So when managing the change stream, we typically recommend using full supplemental logging when at all possible. This is by far the simplest way to ensure that full data records are available to the Kafka consumers. However, this approach may not be feasible in some high-end applications due to the additional overhead required to capture, read, and transmit the whole row on each change event. So GoldenGate also supports partial supplemental logging, where only the change data itself is transmitted. But this, of course, creates its own set of challenges. When partial supplemental logging is utilized, one significant issue to overcome is how to reproduce the full record in Kafka if your consumers require it. A solution to this problem is included with GoldenGate. GoldenGate for Oracle includes access to active data guard for the Oracle database, and data guard is an example of a physical replication or a block level replication tool that can easily create a read standby system. The read standby system can then be used to join back to the partial supplemental records, which are being processed by GoldenGate and the GoldenGate stream processing platform. So GoldenGate, of course, which we'll learn about a little bit later, includes a stream processing engine that happens to run in Apache Spark, and this can be used for the real-time ETL or the real-time merge process to reconstruct the full records into a downstream Kafka topic. So this pattern is particularly useful because it enables the smallest possible workloads on the source system of records. So if you have a heavily loaded application that cannot afford any additional workloads, this pattern can be quite useful, as it allows you to propagate full database events downstream to your Kafka consumers without having to do any SQL operations on the primary system. So you're basically using the standby system to take that additional SQL workload. So that's something that we've seen a number of customers successfully use with the stream processing environment. However, there's another wrinkle to this, which is in some cases, the team that's running the streaming environment or the team that's running the data lake environment may not have the luxury of operating a standby database on the source system, or maybe you've got hundreds of source systems and it's not feasible to create additional standby systems on each of the sources. So in these cases, if you can't access the read standbys of the source, you may need to use the historic messages in Kafka to merge data into these updated views. And in this pattern, we depend on a local cache of message offsets tied in with basically the keys of each record. And this can provide a reasonably fast lookup to fetch the previous full record that's already in the Kafka topic. And then the stream processor can be responsible for doing the merge operation, bringing the full record together with just the change columns that might have been propagated in by the partial supplemental logging. And so at the end of this merge process, the new message would be placed into the Kafka topic as the latest offset, and then it becomes the source for any future updates thereafter. So obviously this produces a lot of events, and topic compaction would have to be run periodically here to prune old messages out of the topics and keep this fairly slim in terms of how much data is held in the Kafka storage tier. So those are a couple patterns that we see around customers looking to create and preserve full records in their Kafka topics. And we'll shift gears now into a little bit of discussion around deployment topologies. We'll probably move fast here. From a deployment perspective, GoldenGate can run entirely on a mid-tier host if that's what's desired. there's zero GoldenGate install footprint required on any of the source systems, right? So the architecture is completely decoupled from the source systems, and it can also be completely decoupled from the downstream Kafka environments. The GoldenGate process is relatively small in the context of most enterprise software. It's more like an agent process or a daemon process. In the newest versions of GoldenGate, it's entirely microservices driven. So you actually have the flexibility, and again, one of the hypothesis I raised at the beginning of this webinar is that the entire world is shifting to distributed architecture. What you can do with GoldenGate is you have the flexibility to operate it in the source systems. You can operate it on the target systems in your big data framework, or in the picture that I'm showing you here, you can operate everything together on a mid-tier. So really, decoupling that the physical installation and administration of this infrastructure. Now, maybe for a future webinar, we'll talk a little bit more about edge processing, IoT, and 5G. But one of the benefits here is that you don't have to think of the world strictly in terms of your data centers. It's not just about your public data centers and your private data centers and your public clouds. You can also begin to think about doing more of this event-based capture and event-based processing on edge systems as well. So once you add the stream processing environment into this, it does add that additional tier for Spark-based data pipelines. If I looked at that stage process where we were describing some, how to go from partial supplemental to full records, this is the type of physical topology that you might need there, which you have the GoldenGate tiers basically doing the partial supplemental logging from the source databases, producing raw events into Kafka. And then you have these pipelines that would execute in a streaming Spark context that would be responsible for the merge operations or any ETL operations for doing additional aggregates, for example, on the events. And so all of that can be deployed across a general purpose open source infrastructure running Kafka and a Spark. And realistically, this chart is pretty generic here, but we've had customers run exactly this architecture fully on Amazon Cloud, fully on Oracle Cloud, using certain components from Google Cloud or Azure Cloud. So really, it's pretty flexible. What you generally need are sort of vanilla Kafka APIs and vanilla Spark APIs, and then the physical properties of where you locate these different tiers, it's pretty much up to you. So it can be quite flexible, and in that way, again, we're trying to adhere to our philosophy of supporting a very highly distributed architecture that can run across whatever physical data centers you're choosing. So the final pattern that we will briefly mention here today is around the data architecture itself. So we're seeing a fairly common use of Kafka topics to host data at different levels of fidelity. I talk about data fidelity here in the context of how much detail you want to see in your data records, or more specifically in your data events. So very high fidelity information has event by event metadata, event by event detail that's typically going to be at the exact same level of fidelity or semantics as the raw data formats coming from the producer systems of record. So in the case of databases, you're going to see all of those, all the metadata and the frequency of events that are coming from the logical change records. And so that winds up being super valuable if you're a DBA or even a data scientist looking to build regression algorithms on user behaviors. But often this very high fidelity data is just too technical for many data consumers and for many data product owners. So thus, what we see here pretty typically is that data engineers may be responsible for creating prepared data views or canonical data zones where the data has been aggregated and formatted to be more in line with the business object definitions that the business consumers may expect. And so you may be formatting to, again, make full records available in tabular views. Most people today are comfortable working with tables or spreadsheet views of data. And then there's the data object view, which may be more of a reflection of the types of business objects that your business consumers see in their applications, rather than the physical structures that reside in the storage tier. So obviously, the more processing that's done to these events, the more latency that is added to the end-to-end data pipeline. But even at this scale, working with dozens or even hundreds of database sources, the end-to-end latency that we're talking about here is still in the single-digit seconds for even some of the most complex event processing patterns that we see. In fact, many of our customers measure their end-to-end data flows in the terms of milliseconds rather than seconds. And so you can, depending on the scale of infrastructure, how fast your network is, how much compute you dedicate to the different tiers that are running the enterprise software, you can make this pattern very fast in terms of latency. So there are very few restrictions there. So yeah, this is a pretty typical pattern that we see. It may not always involve Spark. In some cases, it may not involve Kafka. And obviously, there's other technologies out there. Just to be clear, I think, in my opinion, for something to be a pattern, it should be able to be materialized using different kinds of technologies. For messaging, we still see people using RabbitMQ in the open source context, or even JMS systems. Another open source big data framework that's gaining some popularity recently is around Pulsar. So we see some customers experimenting with Pulsar, has some benefits around transaction management. And then from a stream processing environment, there's so many choices out there, whether that's, historically speaking, a lot of historic investments around Apache Storm. For example, we believe in Apache Spark Streaming, and I think from a community perspective, Apache Spark Streaming has the largest community on the planet right now, but certainly others are experimenting with different technologies such as Apache Flink, and then there's a lot of different proprietary technologies, for example, KSQL from Confluent and others that are kind of more vendor specific. So yeah, lots of different ways to implement these patterns, but I think that's what makes them a pattern, is that you can use different technologies. So all right, now that we've covered a deep dive into GoldenGate with Kafka and some of the patterns that we're seeing there, let's talk a little bit about using GoldenGate with Apache Spark for stream processing, and then we'll wrap up after this section. With the streaming frameworks that are becoming more and more popular, one of the things that we've done is we've made the low-code streaming environment directly accessible as part of Oracle GoldenGate. So your data engineers can go in and select from predefined patterns, working with IoT use cases and database management use cases to produce streaming data pipelines. One of the unique things about this tool is it is an interactive designer. So you can, while you're building out your real-time stages, you actually see the data moving through the pipelines, and you actually are watching the formatting occur on the data streams while the data is live and in motion. And the different kinds of use cases, as we've been discussing so far in this presentation, can range from very kind of database specific use cases, like we talked a little bit about how you might use this framework to merge partial supplemental database logs back to create full records into Kafka. You use the framework for that, but you can also use it for more traditional streaming ETL use cases if you want to do aggregates and joins across different data sets. And then there's the whole universe of kind of IoT use cases where you might be looking at more statistical or time series based analytics based off of non-database events, which could be just general application events or logging events that are being produced by general purpose Kafka producers. So this platform can be used for any of that and all of the above in a nice kind of low-code package. Some of you may not have been familiar with this technology, where it's come from at Oracle. We've actually got a strong 10-year record of intellectual property investment in this area. Historically, it used a different architecture, which may be why you weren't familiar with it. But historically, it comes from the background of running inside of what we call a data grid technology. So previously, it was built around the Oracle Coherence data grid, which deployed inside of large-scale WebLogic clusters. And we have a strong track record of dealing with tens of millions of events per second at scale in this data grid context. And what we did approximately 3 years ago is we looked at the maturity that had evolved in the open source community, and we felt that it was a good time to refactor the core technology so that we can run this event engine directly in the open source frameworks of Apache Kafka and Apache Spark Streaming. So in this particular case, we took all of that intellectual property that we have around querying event streams and working with different windowing functions when streaming analytics, and we basically moved that into an application that runs directly within Spark. So we're preserving our IP on top of what Spark and Kafka provide. And one of the bigger benefits around this framework is the low-code environment. You can have more traditional business analysts and data engineers getting very productive very quickly in this environment. We've had a number of our top customers for this area go from project inception to project delivery in less than 8 weeks. It's a very flexible and intuitive way of building not only the data pipelines but also the analytics dashboarding functions as well in this low-code framework. So beyond the user interface, it's worth pointing out that this particular framework adds a lot of real interesting benefits on top of Apache Spark itself. So one of the most important things in the context of industrial strength streaming of database transactions is that you want to be able to guarantee that you can process your data record by record. You want to be able to understand when events are occurring out of order, and you want to be able to work with checkpointing as an automated part of your stream process. And so the stream analytics application that runs in Spark brings all of these capabilities, whereas if you're in a native Spark streaming context and you're just writing code against Spark streaming, your developers basically have to re-implement these capabilities. So the native Spark streaming is what's called a micro batch process, and within the context of the micro batch, events can get out of order, and there's no real sense of a clock that runs between the micro batch functions. And so OSA, the stream analytics framework, really takes care of all that for you, making it frankly more industrial strength, in addition to being easier to use with the low-code environment. The ease of use factor has been improved by providing this library of built-in patterns. So we can basically create patterns very simply by clicking into the pattern, and then once you select it, it gets generated for you into the pipeline. And so we have a number of patterns that are typical for IoT use cases, or in this case, we're showing you a time series function like A followed by B. Once you add these in, it basically allows you to do point and click operations with any of the data sources or the GoldenGate data streams that have been brought into the streaming context. We also have the built-in geospatial capabilities. What we're showing you here, the tool comes built in with built-in maps that allow you to process lat-long data and build geofencing capabilities based on lat-long, but it also has a flexible tile framework where you can bring in spatial functions that are tied to beacon technology. So for example, if you have RFID or Bluetooth-based location services on more specialized mapping tiles, for example, in an airline terminal or inside a shopping mall, you can also build functions that basically allow you to take events, take actions, and fire alerts based off of any location-based information that you have, whether it's very high level like lat long, or very detailed again like RFID or Bluetooth. By far, one of the most common analytic functions that's done inside this tool is around time series analytics. So looking for anomalies, and so whether that's monitoring, the temperature of refrigeration capabilities, looking at fraud detection, so out of band transactions that are happening in e-commerce or banking. You can look at supply chain functions. We've had customers build complex back order analysis, so where there might be a run on particular goods at the store. I'm thinking water and toilet paper in today's context, for example. You might want to be prepared for looking at anomalous levels of transactions by viewing moving average of events, and then firing alerts or even taking action when the transactions fall outside of the band of the moving average. So these are all things that can be built in directly to the transactions, and again, by far one of the more common use cases for streaming. What we're also seeing pick up quite a bit now is really the use of the machine learning functions in the context of these events. So you can basically bring a machine learning model to production by taking models that have been prepared by your data science team on training data, and then taking those scoring models directly into a pipeline function. So whether you're scoring a customer's propensity to buy, what we call next best action, identifying coupons that may encourage consumers to look at other products based on previous or current purchases. You may have scoring models in real time based off of fraud detection. Remember, these things can be put into production as part of a real-time pipeline. It doesn't have to just be statistical or rule-based functions in the pipeline. It can be any of these complex machine learning functions as well, and we can run those native to the Spark environment that these are being executed in. Finally, on the streaming analytics, one of the key features that's built in for the analyst function using this tool is we have all of the built-in dashboarding capabilities. So whether you're bringing in area charts, pie charts, bubble charts, line charts, bar charts, geospatial maps, you can basically create dashboards of all kinds. And one of the unique things here, again, this is not a traditional reporting system or data visualization system. We're not running SQL queries here. What's happening, these events on these dashboards are being pushed to the dashboard as they happen. So you're seeing a continuous flow of events. The dashboards are being continuously updated. There's no polling here. There's no user pushing the button to request a query. It's not something that a query is running every 1 second, for example. These are live events that are being pushed in. So this is truly a real-time analytics dashboard function, as opposed to a more traditional reporting or data visualization function. So, I'm going to go ahead and wrap up here. I just want to take you back through what we've covered. We started pretty high level talking about this global shift in technology, what's required for digital transformation as industries move into this Industry 4.0 model. We talked a little bit about how we believe that data integration frameworks will be continuously shifting towards this view around a data mesh of cyber physical systems that are linked together in these geographically distributed architectures. We talked about it in this presentation as a distributed CAPA architecture. I think in general, we believe very strongly that our customers want to move away from monolithic systems and monolithic organizations and monolithic IT processes, and more towards these flexible and agile distributed frameworks. And that's where GoldenGate for Big Data comes in. It's inherently a distributed framework that allows you to work with data and transactions on an event-by-event basis while preserving the full transaction semantics of your originating data events, and tying that in with all of your open source or public cloud-based infrastructure where you're doing analytics. And that leads us through what we just spoke about at the end of the presentation, where we have Apache Kafka and Apache Spark Streaming working in combination with the GoldenGate technologies, not just for replication, but for stream processing. And this kind of leads us back to this observation that we can create today an event-driven distributed data integration platform that's industrial strength and enterprise class. And that's very much what we're focused on building out in the GoldenGate area. And I'll leave you with the thought here that if any of you out there are working on modernization initiatives, if you're attempting to work with your business line functions to drive digital transformation, I'd encourage you to think about this concept that you're not going to be able to solve the problems that face you today with the same thinking that we used when those problems were created. To be more precise with this comment, I would say if you're still looking at ETL tools and monolithic data integration solutions as part of your solution for modernization, you're probably not going to get there. I think for making the leap to the new technical curve that's emerging, the new paradigm that's emerging, you have to make that change in thinking, the change in culture, where you now think about data inside out. You think about data as a sequence of events where data is constantly changing, it's constantly evolving. It's not a static thing, and it's not something that can be understood in the context of batch processing. You want to modernize your data infrastructure, modernize your data integration infrastructure. It will behoove you to kind of think differently about what your next gen architecture should be scaffolded on as a fundamental framework. And that's very much what we're trying to do here with the GoldenGate platform. So, appreciate everybody's time today. I hope this was a useful presentation and got you thinking about different aspects of your own data management frameworks. And I'll pause here, and I'm happy to take any questions. So to begin with, on my end, I'm